All right, so we know now how to do 3D how to do texturing with 3D textures. Now let's look into 2D texturing, where of course the basic idea is to take an image and put that onto an object. So this is pretty similar to what we had with the 3D mapping with the lookup table approach. In a lookup table approach, we also use the 2D image first, but we can also do, of course, a lookup table in a 3D texture if we have it, or if we create it, like with this pseudo-random 3D array, that pseudo-random vector array in the Perline noise calculation. And but of course, this lookup table that we did so far was very restricted with this tiling approach. We can also do it in a way that we, for example, have a texture that we map completely one-to-one onto an object, like in this example here when we have a sphere, and the most straightforward example is, of course, the world map. If we want to map the world map onto a sphere, we want to do basically a one-to-one mapping, that is not one pixel to texel, but each texel on the each pixel should have one corresponding texel and not a tiled version like we have it so far. Good, so the question is, how can we do this? And this is actually pretty straightforward. If we use the implicit representation, you remember the implicit representation of a sphere is or you probably remember when I introduced that, I said that this doesn't look as intuitive as the parametric representation of a sphere, but it comes in quite quite handy when you do texturing. And indeed, because the point is that here you have, you have two angles that describe you. With the two angles, you get to one and the other here. Then you get a specific point here. And here you have also a two-dimensional coordinate system. Be careful that you don't get confused. I think the book uses a notation here that I think is a little confusing. They use here also the U and V, but in relation to the texture now. So, but here you also have, of course, one point. Let's see, that's approximately here. So you can do the mapping by just mapping the two angles here to the two coordinates here. But since these angles also represent coordinates, it's pretty straightforward. Just take these, then you reverse it. Don't bother much about this. These are the inverse function of this, the inverse function of the cosine. You need that to get the angle out of this equation, and this is the inverse of the tangents. The tangents I haven't had that, so we haven't had that so far. Tangents is the sine x divided by the cosine x. And this is just the inverse function of it to get these angles. If you have these two angles and then you have on the other side the map, then you just do basically what we did in the very first tutorial with this window mapping. We basically just have two values here and two values here. The two values, the two angles are always in between 0 p and minus p and p. So we basically have two squared windows here that we just have to map, so it's just a simple matching. So this is pretty straightforward, which is why I don't want to go into the details. I even thought about dropping completely, because in practice when you do with shader programming, you usually use triangles, you don't need use spheres. I had it in a lecture last year because last year they implemented a ray tracer, and then you actually model spheres and do texture mapping on spheres, and then this is really a nice example. I left it in because this mapping seems quite intuitive to me in contrast to the tile mapping that we had before. Good, but what we usually do when we do texture, when we do shader program, is of course we deal with triangles, and then we need texturing on triangles. And so we have a 2D texture now, but this is pretty straightforward and pretty similar to the lookup table approach before. We have a triangle, and then we just specify the coordinates of the triangle in the texture. Can you see that here? Yeah. So we have, for example, our triangle with 3 points, three vertices, A, B, and C, that define our triangle. And then we just have to define 3 points here on the texture. And this can be like the triangle can be mapped in any possible way. I mean, this is up to us how we define that. We can, for example, also say, of course, one of the most straightforward thing is to put the triangle in as it is here. But we could also do it in a way that we say we put it in like this. which would then lead to a distorted checkerboard. But if that's what we want, then why not do that? We could, in the extreme case, also do something like this, that we say if this is our checkerboard pattern, we make the triangle so small here that we actually get a line pattern here, because we're only with covering one line of our checkerboard texture here. Of course, it would be quite stupid, because we know already how to make this better with a procedure. We make this very easy with a procedural function, but in theory we could do this. Why not? And so the point is basically we have to define 3 points here. I just called them A star and B star and C star, which are here the corner points, and then we get the color, the texture, the texel value on this particular vertex. And then of course we also want to have the lines in between, and again this is pretty straightforward with what we already learned, because we can just use the linear interpolation for this. And if you remember, triangles, we can represent them with barycentric coordinates, and then if we vary this beta and this gamma here, so again barycentric coordinates, we have a vector A here, then we have the vector B minus A in that direction, the other one C minus A in that direction, and then here this is our beta. Was that B? Yeah. Then this is, if that is B, then this is our beta, and that is our gamma. And if beta and gamma fulfill this condition, then we can get all the vectors that are in this triangle, and by increasing beta and gamma, we can walk along this, setting gamma to 0 and increasing beta, we can walk along this vertex. By setting beta to 0 and increasing gamma from 0 to 1, we can walk along this vertex. So we can do a linear interpolation, and then we don't put the color value here, but we can look up then the positions here in our triangle while we walk along. And we can do the same here in between, and then we can do the texturing with these new functions here along this triangle. Good. So pretty straightforward. And again, of course, it can also happen that when we do the mapping, that we do not end up at position ij, but between 4 of these, and then we can do again a bilinear interpolation to avoid artifacts. Yeah, I already said this, that the shape and the area don't have to match the one of the triangle. We can do it any random way, as I saw it here. We can even do it in a way that we have it outside. Like if this is our texture, we can do it in a way like this, for example. And then we can use, for example, tiling, which with that kind of texture would make sense. But if we have, for example, a texture like this, and here we have, I don't know, a flower or the university logo, and then we say, well, I want to have a triangle that looks like this, where the flower is in the center, then we could also do the texturing like this. We just have to be careful what we do with these kind of things here, that we do not treat them correctly. Good. Yeah. So this is pretty straightforward, but there are of course a couple of pitfalls that we have to be taken care of. So for example, when I used this example here, I basically assumed that you're looking at the triangle straight from the front. So the triangle has the same orientation as the texture, the checkerboard in this case. But of course, this is not always the case when we model a scene, because when we model a scene, we're having triangles representing 3D models. So the triangle might be tilted a little bit, yeah, this is now we're talking about perspective projection later. Normally, I have this lecture about perspective projection before texturing. So, but it's intuitive. You know that perspective changes. If it's further away, the object appears smaller to me, and also if the object is not straight but tilted, it also looks like it's getting smaller towards the end. So if we take, for example, a square and then push it, flip it over, then of course the side that is further away from us is smaller. Now if we model everything with triangle, for example, if we have this square here and model it with 2 triangles, and now we do the texture mapping in a straightforward way like here, then we end up getting here a perfectly match a textured triangle according to this mapping function here. We get a perfectly textured triangle here. But if you look at it, of course, they don't, first of all, they don't match, and secondly, they don't look like they're really matching this perspective of the triangle, because we didn't consider that parts of them are further away from us, so we have a perspective distortion. And to consider that, if we want to do the texturing correctly, we have to consider that and do it this way. There is a chapter about this in the book that explains how you can do this mathematically. I will not like to do that, because to understand that you basically need to know what you haven't learned about perspective projection yet. And the other reason about this is, I mean, there are a lot of things in a lecture where I say where you actually don't really need to know how it goes on, because there are functions and procedures in your shader language that basically deal with this kind of problems. Sometimes it makes sense to also understand what is behind it, because you want to learn also about the theory and not only how to program. But you don't have to explain everything. So this is a part which I will basically leave out, because it is fortunate situation that the graphics, the shader language and the hardware take care of this. But it is important to know that this problem appears, and it is important to know that we don't really have to deal with it. And if you're interested, you're very welcome to look into the book and see the theoretical background behind it, how it really works, and what the hardware really does when you do it. Good. Another thing that you have related to this when objects are further away is that, of course, their size changes. So if you move an object, if you tilt it in a 3D, the perspective changes, but also if you move it further away, it gets smaller. So if you have, for example, if you want to texture a square that is directly in front of you, there is basically just one position where the texture and the object fit perfectly. So you can do basically a one-to-one mapping between the pixels and the texels. Although not always you can do a one-to-one mapping, because even at a perfect distance, you might have some misalignments, or you might not have a perfect match. But in theory, there should be one position where it matches. But if the object is then coming closer, you have to enlarge your texture. If it goes further away, you have to shrink your lecture and make it smaller to fit on the object, because for you as an observer, the object appears to be smaller. And of course, you can do this if it comes closer. Then you have to magnify your texture, which is basically again an interpolation. So you have a point here, and then you have to look into, okay, there are 4 points around this, and these are the closest point around it, and then you can make an interpolation between those. And if you do a minification, then it's just the other way around. You look at, okay, this is 1 pixel, and this covers this amount of pixels in my texture. So for example, this is here 1 pixel, and this covers this area here in my texture. So I have to kind of consider all these colors here to put the color on my pixel. And you see where there's where the potential problem, you probably see where the potential problem here is. If you do this, you have basically a constant number of pixels you have to look at to decide about the color. But if you look at it's a fixed small number. You always have to look at 4 pixels basically to do the interpolation, 4 texels to do the interpolation to get the right color value. But here, this texture, the object can get so small that it's just represented by 1 pixel. So in theory, you have to look at all the pixels of the texture to decide what kind of color is the best to represent this 1 pixel in your scene. And if you have a lot of objects with 1 pixel in your scene, then you can imagine that a large texture and every time looking at all the pixels to just decide this 1 color value is really a problem in terms of efficiency. But of course you could also pre-calculate this, and this is basically what's done with MIP, so-called mipmapping. Here it is. Mipmapping is an approach where you basically take a texture and then you pre-calculate, or there are certain images at a different size pre-calculated and optimized for certain distances, and then automatically based on the distance, on the size of an object, or on the distance with respect to the viewer, in the depth of the object with respect to the viewer, the system automatically takes the smaller texture that is more appropriate, so you save calculation time when you do the texture mapping. And again, this is supported by the hardware, so I'm not explaining what goes on behind it, and this is also more a specific hardware implementation thing, so there is, from the theory, not that much interesting behind it, but it is important to know, and it is of course important to use it, because otherwise your graphic might get very slow. Good. So I hope that gives you a good introduction and overview about the texture mapping in 3D and 2D. But again, you you are supposed to do certain things of this texture mapping in the programming assignment anyhow, and I also of course always encourage you to do a little more, and especially this procedural thing is kind of, I think, fun to play around with, and in general the texturing, the programming is kind of nice, so you can do all kind of nice effects with that, and that will also hopefully help you understanding the theory a little better. Good. Now so far we always used textures. We always used images or volumes of color for your textures. But of course, this idea of having pre-calculated values and interpreting them and distributing them over our object and then interpreting them in a certain way, we can also extend this idea in interpreting the values in a different way. They do not necessarily have to represent colors, but in the end they're just numbers, so we can use them to represent different things, for example vectors, for example normal vectors, and this is exactly what is done for bump mapping. To motivate the bump mapping, if you think about one of the reasons why we do this texture mapping is that certain structures are very complicated to calculate or to model, like a wooden structure, because it's not very regular. But also we have a lot of structures which are very not even, which are like bumpy, so you have a very crisp structure. For example, here I've drawn something regularly, but you could also have something that is like really completely chaotic, like this here. And then of course, if you want to model that, you have like normal, if you want to do light calculation here, you have normal vectors pointing in all kind of directions. So this is really difficult and very inefficient to calculate that. And so this is one of the ideas could be, well, if I want to model something like this, this could be, I don't know, it's an image from the book. It could be a planet, but you can also think like the surface of an orange is also very uneven. So you could also take an image and put that there, but you could also say, well, this effect when I look at it that it looks bumpy is basically because the light reflects differently. I could also change my lighting in a way that reflects this, and this is basically what bump mapping is all about. Bump mapping is basically taking, instead of the normal vectors like this, you take certain field of normal vectors that could be completely chaotic. So you can have something like here. These are all weird normal vectors that point anywhere. But again, if we do this completely random, then we get, like with the proline noise, we get this white TV noise. So it looks very chaotic, which could be useful in some cases. We could do it more structured, like in that case. Then we get something that... What's wrong here? Why is it so slow today? I don't know. Yeah, then we get something that is more regular, like here. So we can simulate this kind of shape by just doing the lighting in a way as if there were this kind of shape. And then if you think about it, if you look at the spot and it looks darker, you have the impression that it goes down because the light doesn't come there, even if the model actually is a flat surface. Or you could do something like here. I said this will create this white noise, but you could, for example, use proline noise to create a field of normal vector that has a certain structure, and then you can use that in your light calculation. And this can create some very nice effect. Unfortunately, the image is a little small, but you can. I will put the link to the slides online also. These are slides of images from some SIGGRAPH slides that are quite nice. And you can look it up, and of course you can try it out yourself when you program it. But the obvious problem with this is, of course, that we're just simulating a shape of the geometry by doing the lighting appropriately, but the shape doesn't change. So if you have something like a surface and you look at the top from the surface, you probably won't realize the difference. But if you have something like this, that you have like spots here, and then you have holes here, and then you can simulate a hole by making the lighting appropriately here. But this here you cannot simulate because you don't have it here with bump mapping. With bump mapping you just have different normal vectors, but still this part will not be cut out, so it will not look natural at the borders. And this is why there is also something called displacement mapping, which is basically the similar idea to bump mapping. The only difference is that you do not use a field or texture of normal vectors that you distort then to create this different lighting, but you actually distort the actual model. So it's basically like this. You have your model here. So this is your surface. This is your texture, where you have the things here. And then you do not use that to change the normal vectors, but you use that to change the surface itself. So you see here, this is up and down. This is exactly the thing that results here. And then you can calculate your normal vectors. So the result is, of course, this is much more natural at the borders. So you can really see the bumps here at the side, which you couldn't in the previous one. But of course, since you have to do more calculations, this is also not as efficient as bump mapping. So it really is the trade-off between what kind of quality do you want at what kind of costs. Good. Another related approach is so-called environment mapping. Approaches related to texture mapping is so-called environment mapping. Yeah. Yeah. The same as what? I don't know what that is. Does anyone else know that? Yeah. Yeah. I can say because I don't know it, but I would assume so. Yeah. So from how you described it, so yeah. Thanks. Good. Okay. Yeah. Environment mapping. That is basically the idea is that we take a texture and do not put it on the object, but we put it on the environment. And the idea is to use that when we have, for example, reflecting objects. So the idea is basically we say, okay, we have this teacup here, and we put it on a table, and it reflects the environment. So instead of like really putting the environment there, we just put an image there, like of you can imagine it. It's kind of let me draw it to illustrate it. It's kind of similar if you have like a large cube, and then you say, okay, kind of similar to putting a photo or wallpaper on your walls. You say, okay, I put here at the top an image with clouds and maybe the sun here. And here on the side I put an image with mountains and more clouds and a tree here. Another tree. And then if I put my teapot here in the middle of the woods and it reflects, usually what you do is you see, look where the light source is, you get the light vector L, and you get the normal vector, and you have your I vector E from where you're looking at. And then the idea is to calculate the reflection vector. So the reflection vector is if you have N here and the I vector E here, then the reflection vector is basically the vector with the same angle here as here. And that is called reflection vector because that is the perfect reflection. If you look at a mirror, then the image that you see in a mirror is exactly at this point is exactly the image from the real world where this reflection vector is pointing to. So if you have your I vector here, you have the normal vector, then you can calculate the reflection vector. And when it intersects with, for example, this point here, then you know, okay, there is a cloud here reflecting, so you can draw the cloud here, and if you do this for the neighboring, then you will see that this cloud from here will be reflected here. And this is basically the idea of environment mapping. I will not go into details here, same as with bump mapping and displacement mapping. It's just to let you know about the idea, and then with the bump mapping you can try it out in the practicals, of course. Good. So, are there any questions? No? Then I would say we can close a little earlier today.